Welcome to Pogel activity PG16B. We're on page 187. Now, in these, part B, we're going to talk about reactions of alcohols as nucleophiles and electrophiles. So, model 1, reaction of alcohols as nucleophiles. So in these two reactions, if I were you, I would get them on my reaction sheets. They're important reactions. You will have to predict products and starting materials. This is called the Williamson ether synthesis. So we have methanol, which is our alcohol, and step 1, react that with sodium. And the sodium 0 means it's a metal. It's not a charged state. And you'll see that it's kind of like an acid-base reaction. We've talked about this previously. We make an alkoxide, and then we can react that alkoxide with alkyl halides. And you've done this in previous chapters. And this is an SN2 reaction that makes equation 1 an ether. So that's an ether product. And then we're also going to look at the Fischer esterification reaction. So go ahead and get that reaction on your reaction sheet. And here we have a carboxylic acid. This is acetic acid. It is the active ingredient in vinegar. And here we have an equilibrium. We throw in an alcohol with sulfuric acid. And we are going to make an ester. And we also have water that we've talked about having to use a Dean-Stark trap to drive that water, Le Chatelier's principle. Okay, let's answer question number 1. In the Williamson ether synthesis, model 1, circle the alcohol. Okay, so here's your alcohol. In step 1, the alcohol is converted to an alkoxide. What is the charge on the oxygen of the alkoxide? You see that? It's a -1. That's the charge. C, which reagent, methanol or methoxide, would be a stronger nucleophile? Did you say the methoxide? And why? The negative charge makes it more reactive. The neutral, methanol is the neutral. That's a weak nucleophile. Okay, in D, in the second step, the alkoxide reacts with an alkyl halide. So here we're reacting with an alkyl halide. And the electrophile, so label the nucleophile and the electrophile in each reagent above. So this is your nucleophile. You know that's a strong nucleophile. And this is your electrophile. And the second step is a what? This is SN2. We have a primary alkyl halide. And we have a strong nucleophile. So we're going to get backside attack. We don't have stereochemistry on a primary alkyl halide. And then we get the ether. So it's a substitution reaction. Draw the curved arrows. So we did the curved arrows for the SN2. If the alkyl halide was 2-bromo-2-methylpropane, well, what is that structure? Okay, so what's 2-bromo-2-methylpropane? Well, draw your propane. 1, 2, 3. And then on 2 you put methyl. And then 2 you put bromo. Okay, this is a tertiary alkyl halide. Because this carbon bonded to the bromine is bonded to 3 carbons. Okay. What competing reaction would happen with an alkoxide? Well, you've got a strong base here. And this is not going to go SN2 because it's tertiary. So you're going to get an E2. This is E2 elimination. And there's your elimination reaction. I would want you to draw that reaction. And I think that's what they're asking you to do in H. So go ahead and draw that reaction, and then you have CH3OH. Okay, so now we're on 2. We're going to look at the Fischer esterification questions. Okay, it says circle the alcohol. We're going to label the carboxylic acid. Okay, so here's your alcohol. And then label the carboxylic acid. So here's your carboxylic acid and the Fischer esterification. Draw the polarity arrow on the carboxylic acid to show the polarity. Anytime you have a carbonyl, you have a delta positive there. And this is the delta negative. So you can draw it like that, or you can draw dipoles like that. Compare the carboxylic acid polarity arrow with the alcohol. Which reagent has the partial positive charge? Carboxylic acid, right? So based on the information, identify what species is more likely to act as a nucleophile. So this will be your nucleophile. And your carboxylic acid will be your electrophile. Draw curved arrows above to show the nucleophile attacking the electrophile for this reaction. Don't worry about the role of sulfuric acid. So you would just draw something like this, like that, okay? And then the Fischer esterification reaction is conducted in the presence of a strong acid. Draw the competing reaction that occurs between sulfuric acid and sodium methoxide. All right, so then we draw the reaction. So if you have something like this with sodium methoxide, or if you have your acetic acid with sulfuric acid, indicate the role the alcohol oxide plays as a nucleophile or electrophile. So here, this would be an electrophile, or I mean a nucleophile. And could go there. So you have OCH3, sodium there. Here you get protonation, so the carbonyl gets protonated. And then you get HSO4 minus. So those are the two reactions that we have. The Fischer esterification is an equilibrium reaction. In your groups, discuss how the reaction can be driven forward. So in this case, the alkoxides play in the nucleophile. Well, we've talked about this. You pull off the water. So this is called Chantelay's principle. You learned it in general chemistry. And if we use a Dean Stark and we pull off the water, so we trap the water in this apparatus. Okay, we trap the water and we pull off the water, and that will drive the reaction forward. Okay, compare the two reactions in Model 1. What is the role of the alcohol in each reaction? So in each reaction, the alcohol is your nucleophile. So reaction 1, the Williamson ether synthesis, the role of the nucleophile, right? And alkoxide in the Williamson ether synthesis. And then in the Fischer esterification, the role is the nucleophile as well. And the sulfuric acid just activates that carboxylic acid and makes it more of an electrophilic. All right, let's go on to Model 2. So Model 2, now we're going to look at the conversion of alcohols to electrophiles. So if we protonation, you take a alcohol here and you protonate it, now it is a leaving group. When you have a leaving group, that makes it an electrophile. This is your protonated alcohol. Another way we can do this, which is nicer, more gentle approach, which is nice when you're making molecules because you have a lot of functional groups. And you might have been working on your molecule for years, months and years, so you don't necessarily want to throw it in acid. You avoid acid conditions if you can. But this is toluene, sulfonyl chloride. I probably did this reaction once a week at Eli Lilly when I did synthesis. So here we have a, this is called a tolsyl, and this is a tosylate ester, and it is a leaving group. So let's answer the questions for 4. Consider the protonation reaction in Model 2 above. What bond is being formed in the protonation bond? In the protonation. Okay, so these lone pairs are coming here, and it's an OH bond that's being formed. The alcohol is acting as a base. Okay, so it's acting as a base, and the proton is the acid. Draw curved arrows to show the electron movement to form the protonated alcohol, and we did that. Okay, what about 4C? For the alcohol and the protonated alcohol shown below, circle the leaving group. Okay. So here, they're showing you just something like this, and the leaving group says circle the leaving group. Okay, so we will circle this leaving group, and that would be R plus OH minus is the result there. Here, we're showing our electron flow arrows there. So if we were to circle our leaving group, it would be R plus water. Which leaving group would be the best leaving group? This would be your best leaving group because it's water. It's very stable. Based on your answers above, determine if the neutral alcohol or the protonated alcohol would be a stronger electrophile. So the protonated would be your stronger electrophile because it has a better leaving group. Discuss the reason why the acid is added to your alcohol in a reaction. The alcohol is added, the acid is added in a reaction to make the OH a better leaving group. Okay, to protonate the OH to make it a better leaving group. Now, 5. Consider the tosylation reaction. So now we're going to look at our tosylation reaction. Toluene sulfonyl chloride acts like an alkyl halide. Thus, the alcohol would be expected to react as thus the alcohol would be expected to act as a nucleophile here. And so those electrons will go up and then come down and the chloride leaves. Okay, so this is a nucleophile. Draw the curved arrows to show electron movement to form the tosylate ester. So this is your tosylate ester. For the tosylate ester shown below, circle the leaving group. Draw the leaving group that will form when the bond breaks. All right, so that's shown there. Let's draw it here. So we have our tosyl group, our tosylate ester, pH3, toluene sulfonyl chloride. And the bond that they're showing you here is this. And they're showing you that you get a very stable, and you'll see that this is stabilized by resonance. Okay, and draw the leaving group that will form when the bond breaks. Draw all resonance forms for this leaving group, the tosylate ion. All right, so let's start drawing some resonance structures. Okay, so these electrons can go here, and they can go there. So we just draw two, just so we can capture them all. Two electron flow arrows. And now we also make sure we have our negative charge. Each one of these should have a negative charge. And we can draw another one here. Those electrons go here, they can go up there. And then we can also go into the ring. No, I don't think so. Okay, so there you go. So there's your several resonance structures. Once your group has reached an agreement on the above question, discuss whether you would expect a tosylate group to be better or worse leaving group than OH. Okay, this is a horrible leaving group. There's no resonance stabilized. This is a great leaving group. One of the world's greatest leaving group, and it's stabilized by resonance structures. Okay. What is the goal of protonation and tosylation of an alcohol in Model 2? You want to make the OH a good leaving group. Okay, tosylate can be done under basic conditions or neutral conditions, and protonations under acidic conditions, and so that's why it's nice to have a tosylation reaction. All right, let's work Model 3. Reactions of alcohols as electrophiles. Equation 3. Equation 4. Write the names of the protonated alcohol and tosylate ester under the corresponding reagents. Okay, so this would be our protonated alcohol, and this would be our tosylate ester. And you can write the O-tosyl. That's accepted in the chemistry community. You don't have to draw the structure. All right, B. The protonated alcohol should act as a electrophile. The tosylate ester should act as a electrophile. Why? Because they have a good leaving group on there. Okay, so they're going to act as electrophile. Label the nucleophile and electrophile in the H reaction. Okay, so this is your nucleophile, the bromide. And here, make the sodium positive. It gives you a negative There's your nucleophile, the cyanide. Draw curved arrows to show electron movement in both equation 3 and 4. I do want to see always your curved electron flow. So here we go. It attacks that carbon and those electrons go. Here, attacks this carbon and those electrons break for your leading group. Okay, draw the product of the reaction of RCH2Br and sodium cyanide. Okay, so here we go. This is our electrophile. This is our nucleophile. And this is going to go here. This go there. And then our product will be RCH2CN plus sodium bromide. And are these the same is the question. RCH2CN, RCH2CN. Yes, those are the same. Once the group has reached agreement on the above reactions, compare the reactions in equation 3 and 4 to the reactions of alkyl halide 7F. Would you expect the reactions above to follow the same mechanistic rules as alkyl halides? Okay, so I said yes, because the OH group, OH2, that forms water, is a great leading group, and the tosylate ester is a great leading group. And so great leading groups like the bromide would follow the SN2. So this is all, and you can see by the mechanism with the electron flow arrows in one step, these are SN2 reactions. It looks like you will have your additional problems on 191 and 192. I want to see the electron flow arrows, I want to see formal charges, and I want to see structures. So I can give you that feedback, which is low stakes, before you get your exams.